Let's transition to our next speaker. Will be given by Dr. Angus Locke from ANGIS. The topic will be open source CFD and geometric deep learning for accelerated aerodynamic optimization and design augmentation. Thank you.
Thanks for the introduction, and thanks for the organizers for inviting us to come and present at this event. It's an honor to come and visit China again, and I think it's my 5th time in China, so always enjoy coming out here. I'd also like to acknowledge my co-authors, Apostolos Krasas from ANGIS and Jacob Lusser from Nevasto. To be honest, they did all the work. I can't take any of the credit, but yeah, I'm very excited to talk to you about the work that we've been doing with open source CFD and coupling with AI deep learning for aerodynamic optimization. So the work is a result of a partnership between ANGIS, who is an open source company headquartered in the UK. The founders of the company were actually at Imperial College when foam was being developed before it was even open foam. So we've been working with open foam since 2000, and so have a long experience and a long relationship with the open foam community. Nevasto was actually founded in Berlin by a couple of engineers who did PhDs in aerodynamics, and one of them worked for Audi and one for Airbus, and they have started a company focused on machine learning and optimization in the CFD space and CAE space. So I'm going to talk a little bit about the context why we're interested in this technology, about the AI techniques that we use, the graph neural networks, the methodology of the computational fluid dynamics, and then obviously the results and some conclusions. So really the context, my background is automotive aerodynamics. I've been working in the industry for 30 years now, and the collaboration between the aerodynamics department and the design studio is one of the most challenging within the whole engineering process of vehicles. And the specific challenge is right at the moment. We are obviously, as a world, we're transitioning to more electrified vehicles. China is really leading the way in terms of that transition. The number of electric vehicles on the road is accelerating rapidly. And electric vehicles have specific issues that we need to resolve. Probably the key one is range, and range is really a function of the aerodynamic drag. We don't care about range so much when we're working in, when we're driving in urban environments. We tend to mainly be concerned with range when we're extra urban, when we're going between cities. And at extra urban speeds, which tend to be higher, then aerodynamics is the dominant loss in the electric vehicle. One of the other things that's happened with electric vehicles is we've obviously got rid of the noisy motor that sits up front or behind you, and so wind noise is far more noticeable than it has been previously. And so wind noise reduction is a key target criteria for electric vehicle development. And the final one is ADAS sensors, so advanced driving automatic sensors. Typically a range of different sensor types, from cameras to radar to ultrasound, but one common factor with all of them is that they don't like getting dirty, and so we need to do more simulation work to understand the soiling effects of the aerodynamics around the vehicle on those sensors and try and ensure that they continue to perform well. So at the moment, we use a number of techniques at an early stage in the program to develop a vehicle. So we use parametric CAD and freeform morphing and parametric morphing to change the shape of the vehicle at an early stage. So the design studio will give us an initial 3D shape, and we'll look at changing that shape and try and understand what impact, what the sensitivity of that shape is to various parameters, and how we can optimize it for aerodynamic drag or soiling or acoustics. We obviously also use computational fluid dynamics extensively, and indeed advanced versions of that, like a joint optimization. But we tend to, up until now, we've been focused on traditional techniques like design of experiments to look at a design space, a parameter space. We also have, efficient coupled solvers that can accelerate that process, but it's still very computationally intensive. And so it takes time, and that affects our ability to communicate with the design studio. So just in terms of the challenges that we have with current techniques, obviously we're trying to find an optimal design with a limited amount of CFD time and resources. We're trying to gain insight at these early stage design choices and how they impact the vehicle performance. And really fully exploring the design space is not feasible. The DOEs that we're running, you're typically running hundreds of simulations. We also typically run transient simulations to accurately predict the flow field around the vehicle. And even with very large cloud offerings like Huawei, the challenges associated with running that number of simulations is quite high. And so the turnaround time is long. And that leads to suboptimal communication between the aerodynamics department and the design studio. Optimally, what we would like is an almost real-time conversation with the design studio so that we can come to a compromise. They're obviously looking to make a very beautiful vehicle and are focused on the aesthetics, and we need to work with them so that that still happens, but that we also deliver the aerodynamic performance targets. So the proposal is that we want to incorporate deep learning. We want to use AI to help accelerate that process. And so we'll continue to use a lot of the traditional CFD approaches, but we can use deep learning to accelerate the communication with the design studio and make it almost real time. So in terms of the case study that we're going to do, that I'm talking about today, we used an open source generic model called the Aero SUV. A number of you may have heard of the Drive Air model, which was a generic model created in TU Munich. And the Aero SUV was a variant of that to better represent larger two-box shaped vehicles. So we ran a fairly traditional DOE on that model, and then we're taking that data and using a graph neural network to train a machine learning model, and then we can assess the accuracy of that, the predictions from that model, and also understand the work scope and the workflow for the process, so that we can best propose to the design studio how to integrate this tool into their day-to-day work. So why did we use graph neural networks? Probably the major reason we did is that it maps directly to the geometry. So the vertices and edges in the triangulated surface of your 3D object map to the nodes and communication paths of the graph neural network. And that gives us flexibility in terms of the different shapes that we can assess. It also makes it very scalable. We can look at objects of different size. And it also captures the spatial dependencies. So the vertices and surrounding edges of the 3D object are kind of mapped to a similar structure in the graph neural network. And so the influence of pressure, for example, of surrounding vertices in the 3D CFD is mimicked in the graph neural network. And another key thing is transfer learning. So one of the advantages of graph neural network is it's relatively easy to introduce new geometry or change the shape of the object and retrain the model with minimal effort to update this new information that's being provided. So in terms of what that means, we had to provide a training data set to the graph neural network, and that's the CFD results sampled onto triangulated surfaces. So we're typically using the VTK object format, both for the surface of the vehicle, where we're primarily looking at pressure and wall shear stress, as well as slices in the flow, where we're looking at velocity and total pressure. The next step in that process is that the surfaces have to be decimated to reduce the effort that's required for the graph neural network. And the solution is mapped onto this coarser mesh. The training then occurs on typical graphics GPU accelerators, like NVIDIA's A100, and it typically takes overnight, less than 24 hours to do that training, at least on a data set of this size. And the way that training works is an initial guess works through the graph neural network, and then we use a loss function and we'll work our way back through the neural network and try and minimize the error that's occurring in the prediction. And that obviously iterates towards minimizing that loss function. So in terms of transfer learning, we're looking at the drive air that I mentioned earlier, and we're looking at correlation data. So for a typical training data set, we get very good prediction of the aerodynamic forces and the scalar fields from the training. And then when we introduce a new object or substantially change the shape of the existing object, the baseline object, then we can get poorer predictions, as you can see here. So the initial prediction is very good. It collapses onto this line, typically within 1% to 2%. And then when we introduce a new object, in this case, a spoiler on the rear of the vehicle, the prediction, it can still predict, and it gives decent results, but the prediction error is larger, up to 10%, for example. But then with a relatively small number of transfer learning samples, we can collapse that data back down towards the line and improve the predictions closer to where they were for the baseline case. So in terms of the specific methodology that we used for this case, we used another open source tool, Blender, to do the morphing. It uses a technique called harmonic coordinates for character articulation to actually map a simplified cage that's around the complex object to the complex object inside the cage. And then we use a number of parameters on the cage that allow us to explore a design space, as you can see in the animation in the bottom right-hand side. So we had 12 parameters in this specific example, covering normal kind of changes that you would get at an early stage in an automotive design process. So we're looking at things like roof height, windshield angle, overhangs, and we then take those parameters and use a Latin hypercube to sample the parametric space, and ended up with 117 cases. We use a Python script within Blender to export all of those different geometries into case folders that look very like a standard open foam case structure. So we're exporting into a constant and tri-surface folder structure, and that then allows us to use another Python script to automatically set up all of the different cases and run them automatically. So after you've done the initial creation of the morphing cage, the process is relatively seamless and just involves running a few Python scripts. In terms of the CFD software, we're using Elements, which is a specific automotive variant of our general purpose CFD code called Helix. That's actually a fork of OpenFOAM and uses a meshing tool called Helix Hex Mesh, which is actually based on AutoMesh, which was the precursor, or Snappy Hex Mesh was a fork of Auto Hex Mesh. So we're actually using a development of the precursor to Snappy Hex Mesh. And the two key developers of Snappy Hex Mesh actually work at NGIS. So that mesher has evolved to have better scalability. We have improved layer coverage. I think Snappy typically achieves about 96% layer coverage for the kind of geometries that we're looking at, whereas with the improved layer coverage, we're up to 100%. And then normally with Elements, we would run a transient DDES simulation to really accurately capture the largely separated flows around these kind of bluff bodies that we're looking at in automotive aerodynamics. But in the interests of speeding up the process for this specific paper, we used our block-coupled steady-state approach, which is a very fast coupled solver using the K-omega SST turbulence algorithm. And this is used by 6 out of the 10 Formula 1 teams because it's very fast. And so we were able to generate all of those 117 CFD simulations, I think, in a couple of days. They basically ran over a weekend. And then we also have an extension to post-processing. So we recently developed runtime post-processing, so we can generate images and VTK objects on the fly as the solution is progressing. And so again, all of the post-processing data, all of the training data that was needed for the graph neural network was automatically generated while we were doing the solutions. And that training data, as I mentioned earlier, focused on two different areas. So the surface of the vehicle, we were looking at mean pressure and mean tau, and then also looking at mean velocity and mean total pressure on some slices in the flow. And so we're actually training on all of that information, and so we're not just looking at the scalar output of, or 1D output of the drag coefficient. We're looking at the flow field around the vehicle, and that's really important to try and understand what's changing when we're moving surfaces around. And then in this particular instance, we use 95% of the data set for training. More typically, you would use about 80% of the data set for training, but again, we were just wanting to do things as quickly as possible to fit in and around our commercial work that we're using our HPC system for. So that was 111 samples, and we used 5% for testing. So you want some unseen data for the graph neural network to check that it's performing as expected. So we reserved six cases for training, for testing rather. And then I mentioned before the decimated surface. So this is done to reduce the memory footprint primarily of the graph neural network so that it will fit on the graphics card that we were doing the training on. And that was a 90% reduction in the number of elements on the surface of the car. So in terms of the results, we're looking at correlation graphs here, where the ground truth from the CFD is on the horizontal axis, and then the predicted CD is on the vertical axis. Almost all of these data points fall within 1% of the ground truth predictions, which is extremely accurate, and we're very happy with that. There were a couple of outliers, one here and one here, which were closer to 3%. In those cases, it was because parameters had moved sufficiently to generate a new flow structure. And so again, if we wanted to improve that prediction, we could do some transfer learning to refine the graph neural network around those specific flow structures that weren't present in most of the training data set. And then we have the same information for lift, and we actually get very similar predictions for lift in terms of accuracy. So for the R-squared for drag coefficient is 0.951, and the R-squared for lift is actually even slightly better at 0.958. And then the second graph is that testing data that I was referring to. So the graph neural network has never seen that information before. We're giving it completely new information and testing the accuracy, and you can see it also falls within the same kind of error bounds that we saw on the initial data set. So they're almost all of them are within 1% of the ground truth predictions. And then this is actually an animation where we're going through, I think, 3 or 4 different data points. On the left-hand side, you've got the initial or the original ground truth CFD prediction of the flow field around the vehicle. And on the right-hand side, you've got the output from the graph neural network. And you can see that certainly subjectively they're almost identical. There are some small changes that I've noticed behind the front wheels. This is a very difficult area for CFD to predict, so I'm not hugely surprised to see some small differences there. But in most of the areas of interest around the front fascia and A-pillar and driver's side door mirrors, and then in the wake as well, we're getting very similar predictions. So this is really interesting for me as an aerodynamicist to be able to use this graph neural network output in my day-to-day activities, because I not only see the change in the drag coefficients as you morph the object, but you actually see the flow field and try and understand what the morphing is doing, what changes are being caused to the flow field to result in these changes in the force coefficients. And then this is a video of the Blender plugin, and this is the really exciting thing for me. So a lot of design studios are starting to use Blender. It's an open source geometry creation CGI tool, mainly used in computer graphics and film industry. But I use it extensively in my day-to-day activities, and as I said, design studios are starting to use it as well. We're actually just modifying one of the parameters there. Can then just click a predict button, and if you look in the bottom left-hand corner, you can see that the force coefficients change within a couple of seconds, and the flow field around the vehicle also changes. So we're getting almost immediate feedback for arbitrary changes in the geometry of the vehicle. Obviously, they need to typically fall within the parameter space that we originally trained on. And one of the things about this data set is we had quite narrow parameters, because that's typically what you're constrained to. When you're working with the design studio, they don't like you making big changes, unfortunately. So here we are making some bigger changes, and this is really to illustrate the fact that not only do we give predictions, but we can also look at the confidence of those predictions. And so if you keep your eye on this area over here, we've made changes that are bigger than the original training data set. It will still give us a prediction of force, and it will still give us a prediction of the flow field around the vehicle, but it also gives us a warning that we're outside the area of parametric space that it's confident in. And what we're hoping to do is, when this happens, if the user is interested in this particular geometry change, is we can just have another button in the plugin that says, I'd like to do some transfer learning, and so you can retrain that graph neural network on this new condition and a few data points around it. And then you will get a prediction back. And as we saw earlier, you don't need as many simulations to do that transfer learning. And so we can relatively rapidly update the model to include this new configuration that we didn't incorporate in the original training data set. So yeah, this tool I think can be extremely valuable in communicating with a design studio. You can literally sit down with them, and either the aerodynamicist can move the surface of the vehicle around, or the designer can move the surface of the vehicle around, and you can look at the sensitivities of those geometry changes for aerodynamic drag, or for local flow velocities, or pressures, and obviously we can come to a compromise in terms of the shape of the vehicle, so that we get the vehicle that looks the best but also performs the best from an aerodynamic perspective. So just in terms of our conclusions, we saw very accurate predictions for data within the design space. So as long as we operate within that parametric space that was used for the original training data set, we get very accurate predictions, typically of the order of 1 to 2%. Once we have that machine learning model, it only takes seconds for it to generate predictions on a new design. And that, compared to traditional runtimes for CFD simulations, where if we're running transient, even on 1,000 cores of a conventional cluster, you're looking at 6 to 7 hours to get turnaround. We've gone from 6 to 7 hours feedback loop for the design studio down to literally seconds. So that obviously makes the whole collaboration with aerodynamics and design studio just much more effective. Where we do stray outside the original parametric space, we can use transfer learning to make the model more broadly applicable. And actually what a lot of the OEMs that are already using this software are doing is training on a large range of different vehicles to try and make a single machine learning model that will better predict across a range of different input geometry. And then we just wanted to point out that the accuracy heavily relies both on the data set that you use for the training. So you have to have well-converged CFD results. If you're not getting good convergence or good stability in a transient data set, then you're introducing noise into the training material for the graph neural network, and then things can go wrong. So yeah, you have to focus on your initial data set quite heavily, but once you understand how to set that up, it's a relatively seamless process. And obviously a lot of the big car manufacturers are generating these kind of CFD simulations all the time, and so you can use both historic and new data to train this machine learning model and keep improving the performance of it over time. So just some key takeaways. This link between open source CFD and geometric deep learning gives better collaboration between the design studio and engineers. It allows for real-time evaluation of different concepts and allows you to explore a wide design spectrum, a wide parameter space. It gives you improved understanding of aerodynamic sensitivities. So even in a relatively large OEM, you're limited on the number of CFD simulations you can do, and those kind of what-if studies that you'd like to do as an aerodynamicist, you don't get to do as many as you like. With this tool, we can now look at effectively an infinite number of those questions within the parameter space. And then we can enhance the model with a small number of additional transfer learning samples. So that gives us better decision making at an early stage in the program when it's easier to move the surface of the vehicle around. It allows us to iterate to that improved surface faster, so results in improved productivity and effectively reduces cost. We don't have to do as many CFD simulations to arrive at an optimal solution. Thanks very much for your attention.
Thank you for the very interesting talk. Any questions?
Thank you for the good presentation. So I have one question. To be honest, I'm also a user of the Engis Helix, and thank you very much. So I'm interested in the applicability to the urban airflow using such kind of the graph neural network. What are applicability to this technology to the complex urban airflow?
Yeah, I mean, it's broadly applicable. So the industries that are using it at the moment, it's mainly focused on automotive, a bit of aerospace, but there's no reason why it couldn't be applied to any object or airflow. That's one of the advantages of the graph neural network is its ability to take relatively complex shapes and efficiently train on those complex shapes. So yeah, I mean, if you would like to talk to us about outside the session about what that might look like, I'd be happy to spend some time with you to understand what your simulations are and how we can maybe show you how it could work. And it's not only aerodynamics as well. So it's this same AI tool, for example, has been used for crash analysis. It doesn't have to even be simulation models. We're actually working with a company where we're potentially going to take wind tunnel data and train on the wind tunnel data. So as long as you have a 3D representation of the object and then some scalar data for that object in a format that the graph neural network can read, it can be, as I said, it's very broadly applicable.
Thank you very much. I understand basically is the graph neural network can ability to handle such kind of the many the obstacles like urban airflow. Yeah, thank you very much.
Thank you.
Maybe one more question. Oh, then.
Thank you, Angus. A very impressive work. And I have a question. Do you have applied your work in a real auto company in their new car design?
We haven't, because the partnership is very new. Well, we have on one smaller company, but Navasto, our partners, have already sold this software into a lot of the large OEMs in Germany and the United States, for example, and it's being used already in those companies on a day-to-day basis. We are just about to start our first major project with a German company, a German automotive OEM, on this project. But this was part of the reason we did this, was to learn the workflow so that we could understand better how to help our customers as they install this software.
Thank you.
Last question.
Thanks, Angus, for a nice presentation. Actually, I wanted to ask the same question. That was my first question. It's good that it's been answered already. It's good to see you have already deployed machine learning models towards the real industrial design. And for machine learning technique to be fully utilized, we have to go towards large data and large models. How do you see the possibility to have a large data set like those guys did in image recognition, this ImageNet kind of thing, which was really the milestone for the breakthrough in AI. Whereas for this, I think it's difficult to have publicly available large data. Then that brings another question: do we have enough computing power to generate so much data out of our customers or our own computing power? How do you see this? Because I think this is essential for this to be truly generalizable and transferable.
Yeah, I mean, obviously the big automotive OEMs have far more compute power than we do, unfortunately. So they have tens of thousands of cores available to them. And they also have historic data sets. So that's the great thing about this, is the input data is not particularly unique. within Elements, we tend to export this data routinely. So I did a project over the last 3 years with one of the EV manufacturers, and they routinely export the data that could be used. And so all that data that they've been generating over the last 3 years, they could use as a input for training data. So it's not like we're starting from scratch and have to generate all of this data anew. And then we also have a very fast solver, so that's one of our advantages, and so even to generate transient data sets, we can do it relatively quickly. And then with people moving to the cloud, like Huawei Cloud, that obviously opens up the opportunity to use a large cloud resource to potentially train or to potentially generate the training data set, and then even to actually train the model. I don't know, I mean, I think normal data sets, initial data sets for this can extend up to sort of 300 or 400 training points. I don't know if you started with a training data set of many thousands of data points, how long the graph neural network would take to do that training. But I believe we did this training on a single NVIDIA A100 overnight, so it's not like it took a lot of time. So yeah, I think we are going to see OEMs trying to move to a more generally applicable model, and hopefully that doesn't take away too much CFD work, because obviously that's where we earn our money.
Well, we'll still need the CFD engine to generate new data. So,
yeah, exactly. I think there was a question at the back as well.
Herb, you want to have a last question, I guess?
Hi, sorry about that. Thank you, Angus. That was really interesting. I wanted to ask you about the coupled solver. Can you give me a feel of how it behaves? Does it blow up? Does it cause trouble? How many iterations does it do? And also, if you could tell me about the quality of the solution that you get from a steady state solver operating on something that's really transient. Okay.
Yeah, so the solver is very stable, and actually we've recently upgraded it to use a local time stepping approach that improves convergence. Obviously with a lot of the F1 teams, I'm not sure if everyone in the room knows, but they're constrained on the amount of compute time they can spend with the sporting regulations for that series. And so they're looking for us to improve the performance all the time. And it was already very fast and tended to converge nicely, but the local time stepping has improved that further. In terms of whether we would normally use a steady state solution for this particular vehicle type, no. We provide templates and Elements that encapsulate what we feel like is our best practices. So everything from meshing to solver settings, and also a turbulence algorithm. And we typically use a spell-out Almaris DDES approach. That's been heavily validated. So we have a partnership for that product with a wind tunnel in the United States. And we validated hundreds of different vehicle configurations and found that the DDES approach was the one that gave us the most consistently good results across a wide range of different vehicle shapes.
All right.
Thank you.
I guess let's conclude our session. Let's thank Angus, and also thank all the speakers in this session. Let's give a round of applause.
Thanks, everyone.
Just a quick reminder for those attending the banquet. We have the shuttle bus now available just at the exit of the sub-venue. We don't have to go to the southeast gate anymore. So after this afternoon's session, if you're going to the banquet, just come to the shuttle bus in front of the venue. Okay, thank you.